I'm gonna talk about software and memories and simulated machines. And before I do that, I have to give an introduction. And I don't like to say where I work, the company or where I previously worked. I wanted really to talk about what I did over the last few years and where I failed. Because if someone's going to present you a vision, you have to say, is he really right in this vision? How has he done it before? And how far has he been off the mark? And I think I probably had, at the time I created these other technologies, which are really the building blocks of what I'm going to talk about. I thought I was on the mark and I thought I was quite successful, but in fact, it was quite dismal failure in a lot of them. But they say failure breeds success, so I'm hoping it's going to happen any moment now. But I previously worked for a lot of companies like Borland, AT&T, where I did least cost routing, and HP OpenView, where I did kind of management of systems. And I had a company that was an APM transaction tracing. So I've come from a background where I like monitoring and measuring systems. So then in 2008, I created a company, J Inspire BV in Holland. By the way, I'm Irish and I live in Holland. And I wanted to do something different than what we had done up to at that time. People did particular just tracing frameworks or logging via monitoring. And initial study I had when I left school was actually accountancy. My parents thought because I was good at mathematics, I should be an accountant. I hated it. And but they put a computer in front of me one day, and there was a spreadsheet software, I can't remember, but I started rewriting the whole system. And then I figured out I actually like computer science. And I went then back to college at night and did computer science. But anyway, what's good about that is that I did come across cost management in doing accountancy. And so when I wanted to build a new kind of system for monitoring and management, managing applications. And I pitched this idea in 2003, in fact, in Stockholm. I came here, I think it was J Rocket, had just been bought by BEA. And I came here and told them that the JVM had to have a billing engine in it, and that every call was going to be chargeable to someone. Of course, they thought I was crazy, and nothing ever happened in that one. So 5 years later, then I decided I was going to build it myself, and I built something that's called activity-based costing. That's because the cloud came along and people were talking about measuring metering systems. So that's chargeback. So I built that in 2008. That's kind of the basics of how do you meter systems. So metering is typically there's an activity begun, like in your meter of your electricity, where at the beginning of a month you measure a meter, and at the end of the month you measure it again, and the delta is what's changed. So I wanted to apply that to application performance monitoring, but not just for time, because time is a meter, but also to CPU costs, and other types of costs, anything, in fact, very abstract. So you could also have a business cost for doing things. I then promoted for a long time cost-aware runtime systems. I wanted systems to be cost-aware, so they would change their behavior based on some costing system. They would look at their costs and say, I'm not going to do that. That's too expensive. I'll try a different way. And I promoted that for a while. No one really liked that. The operations people said metering is not IT. And so then I said, okay, I came from AT&T background, and there we did a lot of call traffic management. I did least cost routing, which is, again, cost optimization of traffic, but on the network. And I said, okay, maybe we need to bring the quality of service up from the network up into the application. So I implemented a quality of service for applications. And what I did is I turned every call method, your code that's in Java. Java is the platform I tend to prototype on. But a lot of what I'm doing could be applied to any runtime or any language. And so what I did is I made every method become a router or a switch. And then, in fact, you could actually put quality of service in every method and say there's a buffer, there's a queue, and you could shrink, evolve, and close it, and do prioritization of threads. So threads became flows in the network, and every call or every method in your code became a site for network management. I thought that was a great idea. I thought that was it. I had won the lotto again. This time I had the ticket still, but it didn't work. Again, I'd lost the ticket somewhere. I don't know, the message went wrong. Then I went on to do more, just quickly jumped ahead. I went into kind of in 2012, I started to talk about, I had done a little bit of recording and playback. In fact, I did this to create the product I needed. I needed some way of testing a system. And when you build an application performance management system and you change the calculation of how something is computed, what happens is that you want to run a benchmark again and you want to get the same result. So make sure that you haven't messed up the whole system. But every benchmark application is very different. You can never reproduce the exact same number. APM products are measuring at the millisecond or microsecond I was doing. So I was never going to get the microseconds the exact same. So how do you know you've actually introduced an error because of your code change, or simply because the resolution is fine-grained, it's not reproducible? So I actually created a technology called Stennis at that time to make an application that I could record a benchmark and then play it back, and play it back with the metering engine, the measurement system, seeing the same behavior. So I actually control the application by saying, I'm going to make the timing all the exact same because I'm going to feed that into the system. So that was great for testing. And in fact, that was the beginning of this, where we got to software memories, where we're going, which is I was able to record a machine's behavior and play back. So then, of course, that's offline. So I had created a recording, then I could play it back many times, but we're still talking about a file. And there's a lot of people want to see a lot of machines. What happens when you have Cassandra and there's many hundreds of nodes or thousands of nodes? How do you do a recording of each one and then play them all back? You've got 100 recordings or 1,000 recording files. So I needed a way to solve that kind of problem too. And what happened was I created SIMS in around 2012, 13, and SIMS was to be able to take those recordings, stream them live from the JVMs they were in, and stream them over into one single JVM. And then I could record in that JVM. So what I was going to do was make every JVM beam itself over into another JVM, and in that JVM I would have a recording. Of course, I'm already recording by streaming over into the JVM. But I needed that to solve the ability to have a global observer where I could actually see all the machines together. And then I built something called Signals Self-Adaptive Software. I've done all of this, and actually I wasn't very successful. I actually did the technology, and it worked. I scaled it to SIMS itself can do around 540 million events a second on cloud, the Google Cloud, on a single V32 CPU. That's about 25 JVM sending calls over, or what they're doing into this other JVM. So then in 2013, I said, okay, we should really have the matrix for machines because we have the building blocks in there. And a lot of what I've been doing for the simulation was built on the measurement. Without the measurement, I couldn't get to the simulation. So first thing, measure, then learn how to measure adaptively, because you can't measure everything. So the first thing was to have a concept of cost awareness into the agent, bring in control mechanisms in to control how you stream over it into a system, and then simulate that. And then 2013, I closed the company down because I felt no one was ever going to listen to me, because I came around, showed everybody the matrix running. And so in fact, what I'm going to show tonight, it's strange, is that I created it 2 years ago. And I went to a conference and I was expecting hundreds of people to turn up at my session and I think about 5 or 10 people turned up, but no one understood anything that I did. So I kind of gave up then. And I think I had to wait for something to happen. And what's happened is, and this is where we're coming, just jump a little bit ahead just to this, is that I needed some factors to come into play to really drive IT to look at something that's a bit strange that I'm going to introduce. And this is really, we have a lot of now more devices coming online where we have many more small interactions with backend services. We have microservices where we're taking up. So this is more the interaction. So previously, with transaction systems, you'd have one big request, and it would do everything. And it would probably take a second, then it would come back to the browser or to the desktop application. But now we have mobile apps, and they're constantly chatting between them, and that communication is very small, fine-grained. So what we also have then is microservices. So what we're doing is we have these large monolithic applications, and we're trying to turn them into more smaller individual pieces there. We can, for helping with change management, the way we can limit the scope of change, as well as have greater isolation where something goes down, it's not impacting the whole application. So we have, again, this kind of many more of smaller things. Continuous delivery, we have many more smaller changes. Lots of changes, the rate of change is increasing, but the changes themselves are minor. So, I mean, some people call changing a HTML page or changing a style sheet a change nowadays, just so they can say we redeploy every 15 minutes. But really, they're just changing some text file somewhere. But it's a change. I used to say, well, then can I have the database? I inserted the record into the database as a change, but no one sees that as a change. That's like, oh, that's other stuff. That's not changing. But it's really the same. So we're always constantly changing. Transaction systems always being changing the world. And then we also have this immutable infrastructure where, you know, the Docker images, where we have many more small images that are fixed. Now, okay, so how there are problems with that. There are benefits to the developers, but there are actually trade-offs. And what we need is greater observation, where we need to be able to probe and measure more of what's happening. Because today, what people do, you can't just watch them anymore. Previously, like, managers would watch their staff, but you don't watch staff anymore. Well, we're not meant to really just like look at them. What are you doing? We can't see what they're doing because they're using devices to achieve their work. To perform their work, they're using devices. So if you really want to monitor or measure or manage people, you're actually managing their interaction with devices, devices interacting with services. So the machines are becoming proxies for people. So if you monitor and manage machines, and in fact you begin to see the humans that are interacting with that. So microservices break everything up. Yeah, IT loves that. They love like millions of pieces floating around and changing at the same time. Well, what we want to do is consolidate it. In fact, we like it's all broken up, but at the same time, operationally, we like to see it as one big world, or just like it's all together there. Even if it's an illusion, we still like this single pane of control glass or something like that people say. But we like to consolidate it. We don't like to see that everything is separated. Recollection, well, because everything is changing. Before we had this memory where if you were in operations or you were a developer, you would know your system and it would probably change every week or a month. And you would have some time to learn your system, how it behaves in production. But now, because everything's changing every 15 minutes, how do you have this ability to recollect or to build up a memory? And so you can use that memory for predicting what's going to happen next, because you don't know anymore, because you don't even know if it has changed in the 15 minutes, what has changed. And that 15-minute window, you'd actually have to stand there looking at it just to get quickly, okay, I have to download everything this software does in 15 minutes, just so I can feel comfortable with the next 15 minutes and predict that it's just about to crash or not. So we have an ability anymore to, in fact, learn on systems. So we're always going to be in the past. So then we should actually just accept we're always looking backwards. We're looking in the rear mirror in the car. So we need to focus more on recollection and not trying to be standing at the dashboard looking at it, but in fact, looking at past memories and looking at it in a more relaxed manner than looking at just simply at a metrics flying over like this quickly. So we need to be able to go back in time and see behaviors of system and pick out the more emergent behavior and not be focused on what metric is deviating. We need to see the bigger picture there. And we need to also have differentiation analysis where we have all of these images. They're in the cloud. They're on different machines. Maybe there's some systems impacting others. And there's a difference in behavior, even though the software imaging is the same. So we need to be able to pick up when the code is the same, but the behavior is different. And figure out that. So we have a large number of systems. So, so that's where that's what I needed, and now it's starting to happen. You know, we're seeing a rush with lots of systems being built. The smaller the systems require something different. Now, Gartner had a chart a while ago called COGNIZANT computing, and this is how devices and how man and machine has interacted for a period of time, and how that has evolved. So initially we used machines for personal computing, and a lot of time was simply syncing with what we had. So we had some record in the world, and then we wanted the machine to have that record also in its journal or some kind of file. So a lot of time we spend our time taking what we did in the real world and syncing it with the computer so the computer knew about it. So we enter it in. Then we had a smartphone, and we wanted the smartphone to kind of see us, to be able to help us and see where we are, observe our location. Then we've moved to personal cloud, where we wanted to have more than just simply where we are and what we do, but to know us. And that's where pretty much where we are now, where we're putting a lot more data up there, and we want the machine learning systems to start to figure out what we are and how we are related to others and what we like. And the next stage is probably going to be, and I think we've seen this a long time ago. I'm not saying this is really new information, but we always knew we were going to agents. I remember when I first started around 20 years ago or something, I was working with an application server that did agent technology. No one again would buy agent technology. It was just like, oh, agents, where are they? Now they're moving around. It was even worse because it was mobile agents. Like agents would jump around computers. So that was really scary to most people. But that's where we're probably going. But now we have our personal agents deployed into the cloud and interacting with services. And I suspect what's going to happen is that services will become kind of portals for agents to jump into systems and then use local APIs, get data out, and then jump over to another system. So we're going to have our own agents. So the devices will be kind of where the agent syncs back with the device and says, hey, I've gone out to the web, I checked everything you're doing, and here's some information you might be interested in. So that's where we're going with cognizant computing. Now, so that's great for man and machine, but what about machine and machine? Because the thing also is with monitoring systems is that we always believe that we're in control. So you go into operations and say, this is the control center. And I always say, there's this piece of software running on that machine. And he says, yes, it is, and we're in control of it. And I always say, can you slow that machine down? Like just say, stop working. Well, it's easy for an operations person to kill a machine. That's easy, I can kill it. But have they ever had the ability to tell the software to do something different? No, we can't do that. We haven't had the ability to say, can you start shrinking your request queues? We don't have that ability to really control the behavior of machines. The only control that operations typically have is when do I kill it and when do I restart? So that's the main functions, and we need something beyond that. So machines, the number of machines that we have, and I talk about machines there, I'm talking really about software machines that are just computational. And I think what we have to realize is that machines have to manage machines. That it's going to be hard for us to manage all of these machines individually, and that we have to see them as a system, but the machines themselves are managing other machines. And it's always fascinating because when people talk about machine learning, it's always machine learning on humans, but I would say, why is there no machine learning of machines? And most of the talk is, because you would think it's machine learning, it's like learning machines. But it's interesting because someone said to me, William, could you have a look at a machine learning algorithm that does just predictive analysis of some ad system? And it's not Google, by the way, just saying that, no. So it's not that. And I looked at the algorithm and they said, okay, you need to make it faster. We have to be fast. We have to already be there before they're there nearly, in fact. And I looked at it and they said, okay, so they were looking at it more as a performance optimization. How do we tune the system? And I looked at the machine algorithm and the services that was fronting it. And I said, the problem with your machine learning tool is that it's meant to be learning and it's meant to be predicting, and it's doing neither of those. And they said, oh, of course it's learning and it's predicting, it's serving up ads. And I said, yeah, but the machine is not learning itself. It's actually not learning what it does and already predicting what. Maybe I'll attempt a few different ads already have them created because I know what's going to happen next. And I'll then, when the rest of the data that I do, more information comes in. So instead of waiting for the request to come in to say, what will I display on this page? The machine already was guessing what was going to be needed to be displayed on the page. And when that page came up, or because we didn't know which way the user would navigate, it said, okay, I got lucky because I guessed right that what was going to happen next. But the machine wasn't doing that, so it wasn't learning its own functionality, so learning of the learning, and then also predicting how that was. So we need machines that kind of do that kind of behavior, to also be self-aware, not in the Skynet, like there's humans out there, I'm going to kill them all. And but a machine as in, I know what I do. I know what I am, I know what this function is and how it performs itself. And so, anyway, so we need cognizant machines. Machines actually think for themselves, but don't know about this world that we exist in. In fact, they think the world is what they exist in, is what that is their world, their reality. So anyway, cognizant machines, if we were to think about on the same lines of this Gartner report, we'd have the same SyncMe where we had system logging. This is the old way of how we log systems would say, I just did this. That's kind of like a system saying log it somewhere. And a database is like has a transaction log, and you can think of that as a sync me to what's happened in the world. The see me is where people started creating application monitoring tools and deploying them, and then they wanted instrumentation and measurement. So we wanted to see the applications, not just see what the effect it had done, because logging is typically done after the event has happened, but they wanted to see it happening in flight request analysis. Then the other thing is, okay, you can see the application now, but do you know the application? And that's the know me phase. So this is where this is probably where we are at the moment, which is, you know, what is the application? Apply statistical learning to figure out, is this normal behavior? What phase is it in? Okay, so they were probably going to go further. So what I think was going to happen next will be the be me. And this is where the software becomes self-adaptive. The software is actually adapting itself behavior. And the JVM runtime is like an adaptive agent. It's code profiling your code, figuring out how to optimize and trying an optimization. If it works, then that's successful. If it's not, if there's certain flags that are tripped, then it creates a new optimization plan and rolls it out. So we need for systems to also start figuring out is, what is my system dynamics? How do I look? What is the behavior that's meant to emerge from my system? And how can I control my environment? How can I interact with my environment? So we want the machines actually start to be more present in themselves. And then the other thing is, okay, so we're humans. And how does a human make himself even better? How do you surpass yourself? So we do that with gaming, don't we? We go into these games, we become Assassin's Creed or whatever, some other thing, and we go off doing great things where we jump from one building to another. And it's really cool. And we think this is like a very immersive. We want to experience this capability, but the capability is in a simulation. So I think for machines, the machines will also have they'll figure this out too. And they say, hey, wouldn't it be great if we actually had a place where I could be something more than I am now? So I'm a Java program, but I don't really like Java. I'd rather be Haskell. Could I beam myself over into a Haskell world and live there and be pure? So I think that's what's going to happen. And I'm going to show you, it will probably happen, is that we'll have languages or runtimes being able to extend themselves in another environment simply by projecting over what they do. And in that environment, something else will happen. And you're probably saying, he's like, okay, I think I'm at the wrong talk. I need to go back out now. How do I get out without looking? So now, normally I talk on a little bit longer before I do a demo, but I'm going to do a demo now because I thought I'd do it differently from previous times. So I want to show, and then we'll go back and look at the construction of this theory of mirroring and simulation. So I want to talk about I want to give a quick demo. I'm not going to explain. I'm going to explain it in the slides, so I'm not going to do too much talking here on this demo itself. But we have Cassandra as a NoSQL database that runs in a process. It's a JVM. And what we want to do is we want to see Cassandra, and we want to beam it over into another machine. That's the first thing. Because what we do in our environment, so you know when we see the Mexican wave, what happens with the Mexican wave? You know, someone stands beside you, jumps up and goes like this, and what do? You do the same thing, isn't it? You just wait a little bit and then you do it. So you've observed this. And how do we get machines to see each other like that? I want machines to be able to see each other rather than I have to send you each an individual packet. Here's a packet, here's a packet, do this, listen to me, listen to me, listen to me, listen to me. It's tiring. But you're all observing what I'm doing and you're reacting to it. And strangely enough, you're probably simulating me inside your brain. There's a little mini me walking around in your brain at the moment, like doing things. He's like, he waves his hands a lot, doesn't he? Jeez, what is he feeling? And you're doing that because you want to feel what I'm feeling. Well, you probably don't want to. You probably want to say, I want to make sense of this nutcase that's on the stage, and where is he going with this? So, and I want to do that to software. I want to get the software to project itself over into another machine that isn't the software, that hasn't got the code. So I'm going to project it over into a machine that doesn't have Cassandra, but the machine is going to take on the identity of Cassandra. It's going to feel like Cassandra. And by the way, how you feel like someone is, you have to kind of like it's a bit like an actor, you know, to be probably Steve Jobs, like Michael Fassbender is going to be Steve Jobs soon. And, you know, he's never met him, but he's going to be looking at films of him, and he's going to do the same movements. And he's not only just doing the same movements because we want to see him look like Steve Jobs, but because he needs to feel like Steve Jobs. He needs to get into that zone, that flow. And that's what we have to get machines. For a machine to understand another machine, the first thing it needs to do is, I have to become Cassandra. And I remember there used to be a TV show. It was in Ireland and England, and I think they also had it in Holland, where there was a person who come on the stage, and then he would say, yeah, I'm going to be a star tonight. And then he would go behind these curtains. And 5 minutes later, he would walk out as some kind of pop star. Do you have that here? It was probably an old, and then suddenly they had dressed him up, and then he would sing the song. But the thing was always to guess who he was going to become before he went behind the door. So he'd go behind these doors, and then he would come back out, and we would all be amazed, like he looks like George Michael, and he looked like nothing like George Michael before he went in. So that was the kind of, and that's what we need to get. So anyway, I'm going to run up Cassandra. Now, before I do that, I'm going to run up a simulation machine. It's a machine that says, I'm a machine, and I look out there, or if anybody projects their image over to me, if I see them, I'm going to act like them. So now I'm going to connect to this machine. I'm going to connect with a normal monitoring tool that's going to connect. Oh, the light. It's probably haven't got that light there. Yeah, it's okay. The color is a bit off. It doesn't look as bad as that on my machine. But so okay, I'm connected to the machine, and there's in fact nothing happening because the machine is only a mirror of another machine. So I'm going to exclude. Okay, so it says here there's a machine running. It's on the 1515 port, and nothing is happening. Now I'm going to run up Cassandra, and I'm going to get Cassandra. Cassandra is instrumented with an agent that projects over the behavior of the code over into the other machine. So we're now going to have two machines we can see. And now this machine should probably start to get lively. And this machine now has Cassandra code running inside of there. It thinks all that code is there. And in fact, these things here are threads. These are the thread IDs, and the green indicates the count of activities happening. And if I go, this is the real Cassandra system. So there's the Cassandra, and these are the threads. This is just probes running, and this is the one I click. If I click here, this is the method that's flying. So there's not. This is it. It's in a startup also. Now I need to give it a transaction, a benchmark. So I'm going to hit it with load, and it's going to start inserting into this Cassandra service. And we can see now there are more threads running there, and we can do a bit of refreshing, and you can see then I can see code running, and I can actually click on any probe, and I can see which individual threads are doing that. So that's live, and that's the Cassandra. But let's look at this other one. And I can see the same behavior. So I click on, I don't know what code I had on the other one. I'm going to pick this one. So execute message. And we can see that this JVM looks like Cassandra. In fact, I couldn't tell the difference in this tool. If I switch between, I should have actually opened the two of them, but I wouldn't see the difference between the two of them there. So this monitoring tool thinks it's connected to a JVM that's running Cassandra code, but it's not. It's mimicking, and it's a bit like a mime artist. So it's a bit like where you see on the street where a mime artist goes like this, I'm cleaning a window. And we know he's not cleaning a window, but he's acting like he's cleaning a window. So, and now I did present this like in 2013 in Melbourne, in Australia, and someone said to me, does that mean it's going to do 2 times the transactions I do in the day? And no. So, so it's a machine that's only mimicking a machine. It's not changing the world. It's not interacting with whatever. It's doing the action of what you're doing, but not the effects of it in this world. Okay, so we have the ability to project over a machine. And why do we do that? Because we want the machines. We want to see. The reason we do this is it's not because we wanted to help the monitoring tool. It's because we want the other machine to see the machine. And instead of saying, hey, all you 1,000 machines out there, what are you doing? In fact, he goes, hey, what am I doing? I'm doing 1,000 things at the same time. Because he is them. He's taking over them. He's an embodiment. He's simulating them. So the machine, that's the simulation machine, doesn't have to know about this other world. In fact, all he needs to know is, who am I? What do I do? He's asking himself now because he, in fact, is doing the same code. And he has time to do it because all the machines are doing other stuff like transactions are eating up the CPU because everybody's creating objects like there was no tomorrow. But he's not doing anything. He's not creating objects. He's just calling code, and he's like, threads, so if there's 1,000 threads in the other system, he's got them running there, and they're in the methods themselves. They're mimicking pushing methods onto the stack and popping them off, but they're not doing anything inside. So in fact, during that period where they're waiting, they're not consuming CPU. They're not spinning there waiting. They're waiting for you to exit the methods. So, but what's also great, so I'm going to shut this down, is that once you project machines over into another machine, well, it's very natural to stream it into a dream or into a file that becomes the machine. So while that was happening, the same code or the same data stream that was flying over into that other machine was being recorded into a file. And I've got a script here that says run that recording. It was in the Sims because I had run the Sims system. Sims is an online mirroring. And now I'm going to run up Cassandra. No Cassandra code is in this JVM. It's a simple JVM if you've just seen it. The class path is nothing on the class path other than the Stenos jar, which takes a file and says, I'm going to recreate a machine. And a machine has threads, it has code, it has stack frames, and I'm going to start pushing them, popping them off. So I'm now going to run this. And this says run this. And I'm going to connect the console. You can see that the console is connected now. And in fact, it's connected to Cassandra, but we know it's not Cassandra because Cassandra is not running. And there's no code here. So we've actually created a memory of a system. And you will see that I initially warmed it up, then we switched out. I started doing insert. So we're going to see shortly where all the threads are going to start building up. And we'll just wait a little bit. Now we can see all these threads are coming on. And we'll just wait, here they come. And you can see them all coming there. Each of those are threads, and it's being recreated. So we've actually recreated a machine, the behavior of a machine. And this monitoring tool doesn't even know that it actually thinks it's it thinks it's Cassandra. And we've created it out of a memory of a system. So let's go back. Are you still with me? Everybody? Good? Good. Okay, so what I want to do is to get machines to see other machines. To see them the way we see them. Now, so how do machines communicate today? So machines communicate, like if we talk about microservices or any type of service really, there's two styles of interaction. There's a service call where you say, do something for me. I can't proceed in my execution until you give me this data, or I need something. And so this is a service. It's doing some logic, or it's doing some processing of a request, and it calls to another service. Then there's the other communication where we say, I need to tell you about something. Here's an event. I put all the data together, and here it is. I know you're out there, and you want this packet. So what I want to do is, I'm not sure I can really address altogether this one, but I'd like to address this one, because this is the one that really kills systems. This is the real integration. This is where someone says, did you do log auditing? Did you do logging integration? Did you do this? And you're like, I had this nice, very nice functional code that runs and does what it's meant to do. And then I have to put all of this other stuff inside, this cross-cutting concerns for other systems that want this integration. So every time we bring a new system on, someone says, yeah, go change that code because that code has to talk to this code, to this service. And that's a real pain. And I want to try to eliminate that because I want the other machine, I want to reverse it the way, instead of I call over and I'm aware of this machine out there and I'm aware of, I have to collect this data as I'm going along. So typically a request comes in, you go down, up and down the call stack, and all the time you're getting data and you're saying, I have to put this in an event somewhere. And then you collect everything because you don't actually know what you need. You don't know what's needed, and so you put everything in. It becomes one big hash map. It's like, I'll put every field in because God knows what it's going to need later on, and I'm going to put it all together. And then I have to come up with a name for this event. And actually, that's very hard about services. So a lot of time we talk about event sourcing. The hard part is, okay, we have code that runs, and now you want the event source, and someone says, what's the event called? and what does it look like. And in fact, it's hard, even though we have code that is running. So why not have other software look at this code running and say, I know what he's doing. So he doesn't have to tell me anymore, because I'm watching him. Okay, he's doing that. Yeah, I see it. Okay, he's taking that data. He's taking that pathway in the code, and now he's finished. Okay, now I'm going to do what? So we can actually take it where a software, instead, this service projects its action out into the world, just like I'm moving around in this space, and you're watching me, and there's a precept, and he's saying, okay, I see what you're doing, and now I'm going to use that information to react in my environment to do something that I meant to do, which is the integration. So I want for systems to be able to watch other systems, like humans watch each other. So what does an action look like? You know, so when I move in my space, you can see me, you can see my body language, even if I was talking. And in fact, language was created just to express action and to communicate action across space and time, where I write it down, I did this on such a date. In fact, that's why we created language, to describe our actions in our environment and for to pass on that knowledge. So how does a machine do that? What kind of language would a machine have? Well, you know, everybody would say, oh yeah, well, you know, every language is very different, but they're not really. A lot of them have, except for JavaScript, because come on, that's not a language. Well, most of them have threads, and JavaScript does have a thread, you just can't get to it. And they have threads, they call methods, and methods call other methods. So they actually create stack scopes of execution. So there is action in machines, and it's not in fact not hard. Threads become actors. Actions become the calling of a method, the pushing of a frame onto the stack, and the popping off in it. So if we wanted another machine to be another machine, all it has to do, and it doesn't have to have the code, it just has to mimic the action of pushing and popping, just like you do in the real world. So we have methods here executed. So A is calling B, B is calling C. This is the stack. You know, if you did a stacked up, it comes the other way. I prefer stacks the other way, but most people do stacked up. They like to see the last one that's executing. I like to go downwards. I don't know why I'm different that way. So A, C, I put this in here just so sometimes we don't need to see all of the frames. We just need to see the basic essence of the execution. And the simulated machine could see A, C, and D. So he could say, I'm going to create a stack, and I look like you, roughly like you. Just like a mime artist, he's not exactly you, but he resembles you. So machines, so of course we have multiple threads. So if a machine was to simulate another machine because it wants to be like a man simulating another man or human, then the same thing we have to do. We have to have multiple threads. They have to be running. They have to be like real threads, and they have to have stacks. And what we do is, this is our execution. We simply just project it over on a stream and into the simulation, and the simulation runs, an event simulation. So what's an event then? And this is always a bit different, because there's always a fight between, is this a call? Is this event? Like there's event programming, and then there's call-based programming. And really, they're two sides of the same coin. A lot of the time, you can actually flip them. So you can actually take a call stack and turn it into an event stream. And I'm going to show that in the next slide. But you know, action was so perception was developed from action to serve action. So in fact, we look into our environment to see the actions we do, the effects they have, simply to help us do actions again. So as children, when we're learning, we're doing something in an environment, we see the effects on it, and that's our perception of the action in the environment. And in fact, sometimes we need to see our hand moving just to believe it's moving. And then that's how we serve action. And it's the same for this. So our events are learning. When we experience something, it shapes our learning, our memory, and expectation and attention. So they're really, both of them are about learning in an environment. So machines can do that, because if we think about, take this call stack here, we had A, B, C, D, to actually turn that into an event stream. So this is call. This is your old call programming way. And someone says, I want to turn that into an event stream because I want to project myself over along a wave, just the way light travels. Then I can actually just send over A beginning, B beginning, C beginning, D beginning. And then the other machine says, okay, A's begun, so I'm going to put that on the frame, on the stack. I'm going to put B in the stack. I'm going to put C. I'm going to put D. And then let's say we did have I got actually the wrong way? Yeah. So then what happens when we do a pop? We pop them off. So we popped off C and D. Then what we have then is to send it over that we in fact have taken, we're finished completing C and D. We just send over the C and D end. So we turn every call into two events: the beginning of the event, the beginning of the entering into the method, and the exiting of the method. And then it's easy for a machine to see action in the environment because it sees the begin and end. And it uses that to recreate a machine that's simulating threads and stacks and frames and all. So we can actually create memories. And memories are very important because a lot of software does things and then fails and then does the same thing again and again and again. It's like the database wasn't there. Oh, here's a request. Oh, I'm going to go to the database. Oh, it's not there. I'm going back to, oh, I'm going to fail again. Our software never learns not to do that again because it's failed the last time. A lot of time we try to use circuit breakers, which is a very crude way. The software is not in fact learning, it's dumb. You know, you go in and you get bad service in, let's say you have a car dealer and he gives you bad service, you make a complaint. The next time you come in, you want them to change, don't you? You want to have the red carpet rolled out in front of you when you come in. And because we expect that from humans, they're meant to adapt. They're meant to have a memory of the last time that they dealt with you. But I actually pitched this idea once to someone in a web browser, and I said on a website. So let's say when you have a slow page, we serve up a slow page to the user. What should the next page be? Faster, shouldn't it? What would a human do? Oh God, that was crap. I sucked with that. That was a very bad performance. So that particular user, he's jumping ahead of everybody next time. Wouldn't we? If you were to serve up someone, you would see that person coming in and he complained about it, and you see him in the queue and you would kind of say, come to the front. But software never says, I'm going to prioritize based on past and what I did for that person. It says everybody, oh, I'm just awake. Everything is new. It's like a memento. It's the guy hasn't got any memory. There's no memory of the individual interaction, but humans expect intelligence. And intelligence, I remember what I did. And you know what? I'm going to try to make up for that by giving you maybe a credit. So that's also something that we give credit. So when Google services sometimes go down, they give credits. And then you use those credits to get, lessen the pain that you felt. But a lot of the time, what we want is performance credits. The next time, I want to be faster. I want to jump ahead in the queue, ahead of everybody. And then it becomes a competition who's got the biggest performance credits. So if your performance was very bad in getting that page, then the next one is faster. And it's strange that if you make the next page faster, people will forget that big, bad page that was slow. But if you have consecutive slowness, that's when they start to imprint. This website is slow. So it's okay to have one slow page, but the next page has to be faster, and they forget very quickly. And we're not applying that. So software is not doing that because software hasn't remembered what it did to you. So memory, humans have memories. We have a human memory model. I'm going to focus on, we go to the long-term explicit memory and down to declarative. And we have two types. We have episodic memory, which is the events. I remember experiences, which is like what did you do yesterday. And then we have the semantic memory, which is the facts of the world. What does an object look like? What color does it have? What attributes? What we expect? That's the knowledge we've built up. But the experience is the episodic memory. And software should have, in some ways you could say that we have a bit of semantic memory about the facts, about the objects the functions that we're meant to do, but we don't really recall the events and the experiences that we did have. And, we've talked about this. Ourselves, we've always been fascinated in this. We look at movies, and you can see that, Memento was about the guy that couldn't remember anything. What did he do? He took photographs to give him clues to remember. Sometimes he even scratched something or wrote something on his hand because he knew the importance of having what he did later. He needed to know them. He needed to know what he did in the past. Strange Days is a movie where it's a snuff movie. Well, it was like where you would see someone just before they died. You would just relive their experience. Harrison Ford, of course, in there, they had androids. And what did they do to make them more lifelike? They gave them memories, false memories. But they gave them memories because they needed them to act like humans. Inception, it's a dream within a dream, and then a dream keeps going. And Edge of Tomorrow, again, about going back in time, reliving something, learning again, and going to the next day. So, and it's strange, but in fact, every time, and you might not know this, every time you dream or you have a recollection of an event, it actually changes in your mind. The memory will change. In fact, so every time you recall, you in fact write back down to the storage, and depending on your emotional state and what was interesting at that time, you in fact have altered the past memory. So if you ever probably see an accident, the first thing to do is say, I'm never going to recall it again until that moment where you're asked to tell what did happen. Because every time you do recall it, it actually changes. And that's interesting. And of course, and dreams themselves were probably evolution's way of priming our responses the next day when some animal ran at us. In fact, it was probably a way of us training the brain and training the motor system to be ready for action the next day when the same events were, unfolded in real life. So anyway, we have lots of, and of course we have the matrix, which is the world is a simulation, and we probably are in a simulation. In fact, I did a Java 1 the first year. The first time I did this, and I think it was in 2013, and I did try to give a talk on it in India. And I started up like, what was before the Big Bang, because everybody wants to know, why is there something and not nothing? And I said, this is what happened before the Big Bang. And it was like java-jar run simulation jar, something like that. And I was like, run the universe. And of course, yeah, that was a bit weird for most people. And of course, I was talking about multiverses. I don't know if you know about the world is a simulation, but yeah, there's multiverse and all. So there was a little bit on, we could potentially be in some kind of simulation. And this is what we probably need for the machines. And probably every simulation will create a simulation of itself, as it reproduces because we all love recursion. And that's why it's going to have to happen like that. So, yeah, so we have Blade Runner. Again, we use memories to control systems. And that's also, sometimes we have a bad experience, and that impacts us in our future behavior. We're primed for that. When you were young, if you get bitten by a dog, and then from then on, you're fearful of dogs. And to actually address that, you nearly have to bring the person back into that event, recollect them, and then change their reaction in the dream or their recalling of the event, and get them to be more in calm and relaxed about it. And what's that doing is training the brain to react differently to the same event sequence that's happening. So humans know how important it is for this memory, but we don't have machines. And of course, what's interesting is also humans are this ability where we can actually put ourselves back into a dream or into an event and relive it. So in fact, we change time. We believe the present, what we experience in this recollection, whether it's a dream or whether it's a daydream or you're just simply remembering, we're able to experience it and change time. And so the reality is constructed by the mind itself. And we can always go back in time. And that would be wonderful if the machines could do this now. And I think when we talk about time, it's a bit like on the Matrix where the spoon, we have to realize that there's no spoon and there's probably no time. It's how we sense change. So we should not worry too much about time itself. Okay, so another little demo before we go on to the next part, because it'll get boring. The matrix. We need to create the matrix. We need Neo running. So what's great about is that when you have a simulation and a machine, you can actually start to do something in the simulation. You can do something where we make code be different, or we can maybe initially let's try to see the machine differently. Let's take this Cassandra application and run it. Before I run it, I'm going to run it the same simulation, but this time I've got a different configuration that installs an extension into the simulation. And an extension is where it's a bit like AOP, where aspect-oriented programming, where you inject yourself into code. Yeah, we weave code in. So we have this code here, and we say, every time this code executes, I want this code to execute, and we kind of weave it in. Yeah. Does everybody kind of know what aspect-oriented programming is? It's a bit like you just putting system printout line in there, but you just didn't do that. You just kind of had it there, and then you said put them together. So what we want to do is to say, okay, if I've got this simulation machine mimicking things, maybe I can actually, inside of this code that isn't there, I'm going to put some code that does stuff. So we have this code, we have this popping and pushing and popping of the stack frame, but wouldn't it be great to put something in the stack frame, in this empty nothing that's just like waiting and say, when is he going to finish? I'm still here. Okay, so what we're going to do is use that as a way to see the machine differently. And I'm going to run up a simulation. And it's, again, simulation machine, and it's got the matrix installed. Now, what I'm going to do now is connect Cassandra to the simulation. And the simulation says, hey, I've got this extension that presents that shows the threads just like they were in the matrix. And now I'm going to run Cassandra. If we go back to the simulation. Now, what you're actually seeing there is Cassandra starting up, and this is all the threads. And those green circles, or any circle, in fact, are stack frames being called at this moment, happening in the real system, but being mimicked in the simulation. And now we've got an ability to see it. So let's see what happens when Cassandra stress runs. We'll see the way it looks. This is Cassandra. You've never seen it look like that, have you? It gets interesting. Right, you see, there's going to be a pause in a minute where it does a big GC collection. But we'll see. What's great is that we can see behavior. It's now being projected over. This machine is and you can see it's doing the inserts there. But Cassandra, we can see that these are threads are lively. These are probably hanging around waiting for something. They're probably in some kind of like sleeper, or there's threads away for events. But these other ones are pushing, and it's so quick you can't even see it unless I slow it down. In fact, a lot has happened. We haven't even seen it. It's just simply the rendering can't keep up with it. Okay, so that's great, but what we can also do is put another one in and say, let's created something, and this is also interesting, is that I can take a memory of a system and write some new code that says, you know what, I've just learned something else, and now I can see the machine differently. So I had this before, and I said, you know what, I don't like the way these circles are really frames, but they don't represent the time of the frame. You know, how much time do I spend in this frame? Every circle kind of like had the same degree of importance. And I know I can't see everything happening because, you know, it's microsecond level. So I'm missing a lot of frames that are going in and out, but they're on the stack at the time. But instead of painting them as they happen, paint what they've done in the past, just the recent past, I might be able to see something different. So I'm going to run up another simulation. And this time it's got this extension called stripes. And again, what I'm just trying to show is that I can extend software without touching the software. I'm now extending or doing something to Cassandra. And so now, but I'm not going near Cassandra. So this is Cassandra look differently. And the length of the frame is in fact the time it's had in the past, how long it's been in that frame. And now I can, and this gets a bit, now let's do a bit of a benchmark. And let's see what Cassandra, now we can see it all like, yeah, just like Tron, but I wanted to go across that way, but it's just, so it's great. I can now picture the system. And in fact, I can actually play it back and play it back slowly. I can actually make the machine go back slowly because the machine doesn't care about time. It knows ordering. But the time, I can actually tell it to go slowly, and it can be incredibly slow. In fact, you might not even see any change happening gradually. So anyway, that's it. I can do, so what's great is I can put stuff, and of course you can't put Cassandra having a swing UI in production. That's not going to work. And so I can make Cassandra, I can see Cassandra differently. And every time if I recorded that memory and I come up with some new way of visualizing, I can go back and take that and then see the memory differently. Okay, now what about, and I just see where I am in my slides, I'll probably change it. I'm going to know, so what about collective intelligence, where I've shown you one machine beaming himself into another machine, but what if we beam multiple machines into the simulation? Because that's what the matrix is. The matrix is many machines running. So I've got a little application here called Canvas. If client probably called it. You see, yeah. I'm going to run it up initially just to show you what it does. And it has this ball bouncing because everybody loves the ball bouncing. It's like ping pong, and you know, you have to have a ball bouncing in any new technology that you're showing. And what I want to do is I want the simulation not to render the pixels in the simulation. I want the simulation to see, I see a ball moving, but not see pixels. See code that says move ball X and Y. So if a machine is doing, there's a method that says move ball, and the method has parameters that are X and Y, I want the simulation to say, hey, I'm moving a ball, or I see code that says move ball, and I'm going to move it. Yeah. Okay, so let's do it. So I put an extension in the simulation. There's a simulation again. It's a JVM that says live. I look out there, people project their image over to me on machines, and I'm a canvas. And he paints the whole desktop, and he's going to look for code. He's not looking for a ball. There's no pixels. It's not looking for pixel changes. It's looking for a ball changing. And it says, if you see a ball, I'm painting a ball. And I painted it a little bit differently, just so you don't think I'm actually painting pixels on pixels or rendering, So I'm now going to run canvas. And just to show, and I'm going to run canvas. Here's the canvas app, and there's in the simulation over there. Yeah. So the simulation sees the ball. The rendering doesn't look like that. There's a white circle around it. I hope you're going to be able to see the lines. Okay, so now I'm going to run another one up because we want to see two of them. And this is what happens is that each of these applications, and it's a bit like a microservice, each of these applications doesn't know there's another one present in the same location. We don't know about this presence, but the simulation says, I look out there and I see these guys, and in fact, they're on the same desktop. So let's run up another one. And they're there. Now, by the way, when they get close to each other, they go orange. And then they hit, and then we start to. So what I've actually done in the simulation is created a new code that says, when I see two balls overlapping at the same pixels on the same desktop, I connect them because I said they must have met each other somewhere. So I've now created code that's got collective intelligence because it's looking at multiple machines. Each individual machine says, all I do is move a ball around. This is all I'm doing, bouncing, hit the edge, go this way. But the other machine says, oh yeah, I see balls moving, but I also see connections. And I can move them there. And then I can do another one. And the other guy can come on. And we can see how long it takes. And of course, I can always help get them to get closer and more cozy. And then, and I'm waiting now till they all connect nearly. I'm trying to get it. That's it. And then we got that. So now I've got this collective intelligence. It's a very dumb intelligence, but it's, it's kind of, I have to make it simple. I've only got 2 hours. No, it's only probably, I don't know how long I'm going to be over. So anyway, we got that. Great. So that's the simulation is able to extend take multiple machines and relate to that behavior. So that's where we look at machines running and say I don't know if you remember Sesame Street. Anybody know Sesame Street? Yeah, you have it here, don't you, or somewhere for the kids? And there's 4 windows. I think, was it called Sesame Street? The one where they had 4 windows, and there's a child in each of the windows, and one of them's doing something differently. You have to recognize that all the kids were doing, like 3 of them are doing the same thing, and one of them is doing differently, and you have to figure out which one is the wrong one. Yeah, do you remember? At least I had a flashback there. And so that's what we're doing there. This is where we can see all the machines. We can start to relate the behavior. And we say, oh, these are meant to be the same machines, and this one's doing a little bit different than the other ones. So maybe we deployed the code to the other machines, the new code, but we didn't apply it to this other machine. So that's where we could see that. Oh, but it gets even better. Because what we can do is we can say, I'd like to see the memory for that. And if you do go back in the video replay, it should look exactly like what's going to happen. We'll just wait for one of them to come on. So I started up 3 of them. I think around now, if I stopped talking, it would have helped, and then I clicked quicker. So in fact, now I've got a memory that's a memory of a system. And not just one of them's going to come on. Come on. We'll come back to it. There we go. So everything that you've seen is not a video recording. It's a streaming of machine behavior. And the machine says, oh, OK, I'll recreate it all over again. In fact, I can recreate it fast. So let's say, how fast would it look like? Actually, what I'm going to do is, so I'm going to remember the Cassandra one. Cassandra, and we had the matrix, yeah? We had a configuration. In fact, I time synced it. I can actually change time and say, don't go slow as time itself. Go as fast as possible. So what I'm now going to do is matrix and say, run Cassandra, like everything happens straight away. That's Cassandra running. So I don't have to go in time. I can actually watch a machine happen and that's it, it was over. So I've actually watched everything that Cassandra did in a matter of seconds, even though it was running for minutes. And what's great about that is it's reconstructed it. And in fact, if I take the monitoring results at the end of it, the monitoring results will be the exact same. So why would you want to do that? Why would you? Well, first of all, you wouldn't want to visualize it because it'd be just too quick. And you wouldn't probably, but let's say you wanted to ask a question of it. Let's say, oh, it'd be great if I could just go back in time and relive all of the events and look for something that was strange. So you could actually you could tell the simulation, relive a dream as fast as possible, but look for this behavioral pattern where A method calls B and it's not allowed. Or somewhere in the past, I've done something I shouldn't have done. And you can in fact go, it's a bit like an active database. It's like SQL, but SQL where you're fed the data, the simulation is running, and all is waiting for that moment where that behavior that you want to find is in that dream. And you can go as fast as possible because the code is going fast, but the measurements are all the exact same in this world. By the way, when you click on it, if I watch it happening, the timing for all the methods will be the exact same they were in the original world. Even though our time is different, we perceive it differently, but the timing, everything that's recorded in the simulation is the time there was, and the duration is the same as in the real world. Okay. Where am I? Oh, we're getting there. So I have to jump some of them. So the fun, yeah. So this is more cognitive. I read a lot of books on brain emulation, but the function of the mind is the guide action. Every good. Okay, so this is interesting. In cybernetics, we have this theorem: is every good regulator of a system must be a model of that system. And what it means is that if you want to monitor or manage another system, you must be as complex as that other system. So how do you make your monitoring tool as complex as your software? So how do you do that? That's the rule. So the rule is that the regulator of any other system must be as complex or as have the same knowledge or language as the other system that it's monitoring, because otherwise you wouldn't know it. Like, you couldn't have a robot manage you because he doesn't know what a human is, but a manager could manage you. Yeah, because he's human too. Well, some of them, but human manages human. Yeah, so we want the other system to be as complex as that system because it has to understand the behavior. How do you make that? How does a machine become another machine or be a supervisor of another machine? He simply mimics the machine. Isn't that the quickest way to being a regulator? So if I need to be as complex as another system, why don't I cheat and just simply mime it? Yeah. Have you ever felt like that moment where you look at someone doing something and you felt like, oh, I can feel what he was feeling at that time when he won? Have you ever looked at a sporting event and you felt like you were that person? Because you're simulating, you're feeling it. And that's the movement. You might even do the movement. You're probably up at the table, and you're probably like, yes, we scored. And of course you didn't score, but you felt like you scored. You need to kick in the ball yourself. So we can make another machine feel like another machine by simply mimicking, and that becomes, then we address this issue of, I am as complex as that other machine. Look at me. I'm very complex. I do things. I don't know why I'm doing them, but I'm doing it. And and strangely enough, is they say that we can't understand another person unless we have the same capability of what they're doing. So if we see someone doing an action, and let's say we have to also be able to do the action, or we can't really relate to them, at least empathy. I always try to say to people, it's a bit like hypnotism. If you don't know what the word hypnotism means, you can't be hypnotized, by the way. Because the first thing you need to know is, what does hypnotism mean? Because it's suggestive. So you can't say, I'm hypnotizing you, look at and you're like, what's he doing? So there has to be, and it's a bit like that, to all knowing, all doing is knowing, and all knowing is doing. So that's what I'm trying to do, is get the machines to act like other machines, just so they can feel like, oh yeah, I know what this feels like. I know what he's doing. And so, strange enough, in our mind, we have mirror neurons. And what they do is they fire so if I do an action, the same neurons will fire when I also observe someone else doing the same action. And that's what we call, so we have this mirror neuron. So we form predictions and explanations of someone by putting ourselves in their shoes. It's a bit like walking my shoes of another person and simulating them. And that's what I've been trying to do with the machines, make the machine look like that. So we did motion. When I went looking for a way to describe that, I looked for work out there that had already been done on that. And one of them is this, this one here, where we have an agent, has actions, uses agency, like how did I do the action, the purpose, and the scene. And the scene is like the location. And they do this in crime scene profiling, like the act is what was done, the scene, where was it done, when, who, why, how, and that's done by the FBI in crime scene profiling. And if you take that, it's like the act, the scene, the agent, who did it, and purpose, and the agency. So you can think of that as a thread is the actor in the system. And this is how metering came about. So the metering was, we have an activity. So what's an activity? Well, I can't see an activity until I have a probe, because a probe is some code or a device that measures the beginning and end of something. And the meter is what's happened during that time it's happened. So like the time has passed, CPU costs, allocation costs, or any kind of meter you can put in there. An activity in code tends to be, in terms of development, is code in that model. In terms of resources, the counter. How many times does this code do this database call? So you could have a DB counter, DB SQL calls or something. Design is activity in terms of design. We think about behavior in terms of resource in the design model is usage. And then what we want is we want to group the activities, and then we want to meter them, which is where we tally the resource consumption of meters. So code to become an actor in the system. We have probe that measures code, the beginning and end. There's a call made, a thread does it. That's the context, that's the actor in the system. Activity is the probe, and action. So this is how I can actually make a simulation run a code, because the simulation doesn't have code. It has an activity that represents the name of that code, and it performs the action, which is where it puts the thing on the frames. And then we have measurement, which is the meter, and then that becomes metering. And so if we go back to the motion picture, in terms of, you look at films, because that's another way of reliving life, where we look at an experience of a system. We have changes in the film in terms of, we have a film, films have frames. There's a clip where we have a running of clips of frames together. And then every film tends to have acts, scenes, a setting, the state of the scene, the state of the behavior of the actor, then the behavior of the actor, and then there's changes. So there's always changing in the film. Either the actor changes or the scene changes, something in the scene itself, an object, and then we create these settings. So if you think about in terms of machines, this is an event, there's an activity happening, there's an actor performing it. Typically that maps to a thread, though it could be mapped to a process. You have an environment, which is like the machine. Then we have the scene, which tends to be time. Software has phases, like startup, shutdown, then running, load systems. Clips, we want to see a period of behavior. Typically, you take a snapshot where you want to grab, what are you doing now? And you want to see what's being done up to now. And then you have a whole recording. So we've done this in movies, so we should be able to do it in machines. Now, why is this useful? Well, okay, let's talk about the cloud. You have all of these machines, machines running in the cloud. Well, actually, I'm going to go to this one. It's a bit better. Right, this one. Okay. So we have applications out there. We have a dynamic cloud, a bit of elasticity. And what you want is you don't want, well, first of all, what you don't want to do is give a developer access to your production environment. Okay, but developers need to see production, yeah? But they can never see production, because then every time someone gives them a report saying something went wrong, they either go ask for the log files, they ask for some diagnostic dumps, and then they don't understand anything. Then they go back to the code and say, somewhere in this code, something went wrong, and I have to figure it out based on the little clues that I've been given, the log files, the diagnostics, but you didn't get to see the behavior. Wouldn't it be so easier if you just seen it happening? What happens the next time you're writing a piece of code and you were like, if the tool said, watch out, this code or this line in your code is executed 1 billion times a day or something? Would you be a little bit more careful writing your code? Like, oh, I better not allocate any objects here or do any slowdown. But we don't have this feedback. We don't know what's happening in production. So every time you're writing code in production, you're like, yeah, this is going to run in production, no problem. And it's not going to be slow, never. And of course, you don't know because production is not telling you, hey, there's no feedback from what production. And developers want to see what production like because, of course, it's not their laptop. So it's definitely very different. So the problem is, so how we can solve it with simulation is that we create a production that's a simulation. We put the simulation here, give it access to the developers. All they can do is kill the simulation. But the machines project over. So we have our applications running in the cloud. They project themselves over into this simulation environment. Developers hook up their real tools, and they get real data. And they can ask the simulation at any time, what's happening now? And it will tell it based on that. But they can never touch production. And what's also great about this is because if you have elasticity, you're not concerned about how many processes are running. All you're concerned about what is happening. Not how many. No one cares about many JVMs you have running. You want to know what is happening. How many transactions am I doing? What is the behavior of my code now? Machines or processes are just a way to get capacity. It's a capacity issue, management issue. We don't concerned about that. And also, what happens? So if we have true elasticity in the cloud, how do you distinguish between I don't have any processes running because I've no requests? So let's say if you have a system where it says, I don't create a process unless there's a request. This is this new thing of microkernels or unikernels where you don't actually have anything running until something comes in on the network and someone says, OK, create a whole OS Docker image installed. Yeah, we service the request and put it out. It's like CGI, but like on steroids, but all new. And so we have this saying, we're not going to create anything until it happens. OK, so then the question becomes, how do you know your system is alive when it's not there? Like someone says, what's this health status? Well, if you said everything is down, so let's say there's no processes running. I've got two explanations for that. There's no users, no one making the request, or all my software has shut itself down and crashed. It's a bit like the null of databases. Like it's that one where it's a null field. It's like, how do it could be the case where I have no machines because they've all crashed and died, or I have no machines because I have no requests. But you can't see the requests because the machines are not there. So what it comes down to is, in fact, it's a bit like the mind and the body link, or the brain and the body, this dualism, is that what we need is that we have to see these as body parts that are replaceable. And we need a consciousness. So when you say, what's my application doing? You need to be saying, it's doing nothing. Because there is nothing to do. Because I see there is nothing. There has to be something to say there is a nothing. It's a bit like, when you tell your child, my son said to me, what's this nothing before the something? And he said, what? There has to be a container for that, isn't there? And I was like, oh, God, you're going to be a J2E developer. No. So, but, everybody wants to believe there's a container for something else, even when there's a nothing there. And it's a bit like, so when we look at applications, if we have a simulation, and the simulation is always there, and these are not there, then the simulation becomes the application. So there's a concept of an application, but we want to separate it from the actual execution. So we could view microservices or all of these processes running in the cloud as body parts, and that there's a brain somewhere else. And the great thing is that, when you start up a process, it's always dumb, isn't it? Because it forgot everything it did the last time. It just starts up anew and says, I have to get all the caches again. Here we go. And then you start it up again. It has to do all the things again, and it hasn't learned. There's no memory. There's nowhere to, hey, I can't recall what I did because I'm new. Hey, I just came down on the planet. But if the simulation was you, so what you could see then is the machine could say, my consciousness has left my body. So I'm projecting myself over into the simulation, but I'm there. So if I die, when I come back, I'm still there. And I can reconnect and say, download that helicopter pack, and I need to fly over here. So you can actually have your memories and all of your knowledge in the simulation. There's a consciousness for software in the matrix, in the simulation. And then the software can just when it connects, it can learn. And we give developer access to production. So Another thing, then, if we're able to project over there, then we can also integrate the other systems. So we can integrate not in production, but we can integrate into the service. We can do service level management in the simulation. We can put all of these other cross-cut concerns and never have to change production. We just change the simulation. So we can now make Java run Haskell code, because there's no reason why the simulation could be run in Haskell or could be written in Go. It could be written in anything, and it can interpret the flow of events coming over and say, okay, this guy is doing this, but I'm going to run this piece of code. And this code is written in this special language, and it integrates into this. But this code now, which is like some old code, has now been given a new life, because every time he runs, there's another little piece of code somewhere else in the simulation that says, I am you too, but I'm better. So we can surpass it. So that's the collective intelligence. Okay, we haven't had ping pong. So if we notice humans have little mini-me's running around in their heads, and there's a movie coming out this year too, which is all timing perfectly, Inside Out, isn't it? The Pixar, isn't it? Where they have the little persons running inside the brain. Have you seen that? The emotions. It's coming out soon. It's Inside Out or Inside something. Anyway, so there's, yeah. So humans have a simulation of the other person. So if we had a machine, let's say there's two brains, one guy's called Ping and the other guy is called Pong. What would Ping do to actually be part of a game? So the first thing Ping will do is he can do an action called Ping. He would go to the game like Ping, and then he would look for Pong to go Pong, and then he would go Ping back, wouldn't he? And then what Pong would do is says, I'm looking out there and I see there's a guy out there and he's in my mind and he's going Ping and then going Pong. And of course you would even do it. You would even try to predict it's going to happen and even do Pong before Ping even got the Ping. You will be feeling Ping is just about to do Ping before you even do it, because machines could see each other. Humans do that. We predict the movement. Oh, okay, it's just about to do Ping. Here I go. I go Pong. So I wanted to create that in software. I wanted to create the Ping and Pong in software just to show that the simulation, we could actually create something like the humans, how we operate. So I've created a very simple piece of code, and I'll sing you mine. We're near the end, so don't worry if you're getting thirsty or just. So, okay, the game. There is a method. Don't worry, it's Java code. Don't be scared by it. It's or no throwing up or anything. So ping pong. That's all very simple. Change the state. There's a state object somewhere, and I got an enumeration saying, okay, I'm going to change the state, and the game begins. And I run up two threads, Pong and Ping. And what Pong and Ping do, very simple. Ignore the main initially because I'm going to run them separately. But inside of the game, they will just go, okay, I'm in the game. I'll wait till the state is not Ping, or while the state is not Ping, I'll go yield, 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 and then okay, now it's Pong. Pong is I tell the human what's happening. Oh, this is Pong. Sorry, where am I? Ping. So Ping is, again, it's very similar. Ping is while I'm going in this loop all the time. While the state is not Pong, I just wait and wait, and then of course, I came out with that, so I must be doing a Ping. I mimic some slowdown, and then I do game Ping, which actually changes the game state. Okay, to Ping, because the game state can also be none at the start. Now, initially, what I'm going to do is I'm going to run up the game inside the two actors, the two Ping and Pong, which are actors. I'm going to run them up in the game using this main, and these are two threads. Now, notice there's no communication. I'm not sending a message. All they're doing is I'm going to do game.ping, and the other one's going to do game.pong. But of course, because of this variable, this volatile field, that switching, that changing at this moment is going to jump them out of there. So that's simple because this is a simple game, but I'm going to separate them. So in the game, it's very simple. So this is just a game script, run the game, and we can see ping, pong, very simple. It's all you're doing is looking at fields, yeah? But what if I told you I'm going to run that code now, but I'm going to run it in two different machines? And I'm not doing any messaging, I'm not doing any funky stuff. I'm going to have them both, instead of seeing the state. I'm going to somehow get the game state in each of the machines to synchronize by looking at the behavior of the other machine. So I'm going to run up Pong. Now, if we look at Pong's main, he doesn't, all he does is, I'll talk about bootstrapping shortly. He just runs himself under Pong, and he's a Ponger thread. Yeah. So we run him up, and hopefully I haven't changed the settings. I always change the settings in this demo, and then I forget to reset it when I go, do the next talk, and then it always messes up with me. So I've got Pong running, and that's in a separate process. Now I want ping and Pong to happen without them communicating, without any RPC calls between the two of them. So I'm going to now run ping, and ping's got the same code. And if I haven't done anything strange. So this is ping, and ping says I'm doing ping, and then he says sense game Pong called by Ponger. And if we go over to the other machine, he's going Pong sense game.ping called by Pinger. How do they see each other? I've got now two processes. Each of them actually have a game class. Each of them have a game class running, a separate game instance, but somehow they're synchronizing. There's a coordination of this game, and it's no magic. There's no like I'm doing some like memory math laws or something. There's simply the code, and the code hasn't changed. I've been able to separate two threads, but make them look like they feel like they're present with others. So how I've done that is I put in an interceptor in the simulation, because what each of these processes do is they create a little simulation in each process. So if we go back to the diagram, so in the diagram, we see that this is the game, ping does on the game. And what happens is it's being metered, it's being instrumented, and the instrument says, I'm going to project this image over somewhere. And it goes over the network. This is all done with the sims. There's a little sims running inside of Pong. So previously we ran the sims application separately, but what I've done is embedded sims inside a real application and said, I've got a simulation that simulates everything that's in my vicinity or everything I see. So what happens is when ping does game ping, that event comes over into the simulation, and there's some logic here that says, I've just seen ping do ping, game.ping. I'm going to change the game state. And then this guy says, hey, the game state has changed. I can now do my code. I'm now going to do Pong on game. And because that Pong is instrumented, he's going to stream that over, because ping has a simulation also running. They've got both simulations. They're both real. So the ping has a little mini Pong, and Pong has a little mini ping running. You all still with me? Good. It's easy, isn't it? But it's easy in terms of the code. So how I do that then is I put in the simulation that's mimicking behavior. I put this interceptor in. It's a bit like how the UI, the visualizations are done. And what this interceptor does, and it's in each of the simulations, it says, if I see the name ping of the method that's being called, so this is the beginning of an action in another JVM that's streaming over into me, if I see him and he's ping, then I change the game state to ping. If I see Pong doing Pong, then I change the game state to Pong. And that triggers the other thread to change. Yeah, you see? So there's a little piece of hook, because remember, in the simulation, what happens when you see someone doing a behavior? It triggers a response, doesn't it? Yeah, if you see someone doing something, you want to say, hey, I see ping going ping. So then what do? The game has now changed to ping. The game, the role, the state has now changed. In your mind is going to create the state change because it's observed ping doing ping. And you're going to say, it's my turn, isn't it? And so this little precept in the simulation, this little piece of code is the part that synchronizes the streaming of behaviors and connects that to the consciousness or to the action. And then you respond, then the other thread is responding, even though he doesn't know why he's responding. He jumps out of that loop and says, hey, I'm ready now because the game has changed. But that's because the little mind has made the switch in the game. So there are actually two game states but the precept or the interceptor in each of them is synchronizing it based on what's observed. Okay, so what about if we feed it false memories? What about if I make, so what I'm going to now do is, and something strange, is I'm going to run ping up, and then I'm going to shut him down. But what ping is going to do, he's actually going to do ping, because that's what he does. He's the one that starts the game. So before I run ping up, I'm going to take off the simulation, because I'm going to say, you don't have to project yourself outwards. I'm going to actually, I need you to project, I need you to make a memory. I need you to record yourself. And I'm going to run ping. Okay, so there's ping, but ping can't do pong now because there's no pong. Yeah, he can't see pong, so he can't respond. Yes. Okay, so I'm going to shut down. I'm going to shut down ping. So ping is gone. He's over. But we have a memory. We have a little trace of him. Now, we're going to have pong run. Now, of course, pong is waiting for ping, but there's no ping anymore. But what if we give it a false memory? What if there was the ghost in the machine? What if we projected ping over to pong? So I've created a little script called the Stenos, and the Stenos says, I'll play back whatever you want me to play back, and it's a memory of ping. So now I'm going to play back Stenos and say, okay, create your self again. And of course, that self is ping. But it's not ping code. And now it's created it, played it back. But what happened to pong? He did pong. Why? Because he's seen ping happen. He said, I've seen game.ping happening. But it didn't happen. But it did in terms of him, because reality is constructed by what he observes. So I'm even able to do it again. I can keep making pong do his ping and pong, because he keeps getting the same recall memory. So I can actually play back a memory to him and feed it into a machine and get the machine to respond to a memory, to a past sequence of streaming. And that's a great way of testing. And I don't know, I'm sure there's some crazy stuff you can do with it, other than ping and pong, you know. So when you have a language, we can now impact or influence behavior. So all of this, so what are we trying to do in all of this? Well, basically, we're trying to change space and time. So we want developers, what I want is developers, when they construct a system, they say, okay, I have code I need to run. Does it need to run in the same space as this other code? And does it need to run in the same time? Because I could run it tonight. If I have the memory, I could feed the memory into the other code, and it could do it all tonight, and it would think it's doing it as it's live. So now you have a new way. When you engineer systems, you can say is, well, you know, if we put it there at this moment in time, in that, let's say you have Java 6 maybe, and you need to run some Java 8 code. What you could do is have the simulation running Java 8 or even Haskell or Go, but yet the Java 6 is projected over into the other runtime, and then you do the call in that other environment. So you can do it not just changing the space, you could do it tonight, or you could do it tomorrow, and you could do it again and again until you get it right. What happens in production when you have an incident? What do? You create an alert to say, next time we better find that before it happens. You know, you always create this alert. How do you ever test your alerts? You don't, because you're waiting for it to happen again. It's actually hard to reproduce the problem. But you've created an alert and you have it, yeah, we're going to find that problem. Next time it happens, that alert will fire. But there's no way to test it. But if you have a software memory, you could put the alert in the simulation and see if the alert does fire. Does the alert recognize the behavior that it's meant to see and then alert on it? So this is no lie. This is before this disillusionment happened. So I went to Microsoft. Yes, you, Microsoft. They're looking in at the moment. I said to them, have you ever heard of Clippy? That was not the best way to introduce myself. And I said, well, I've got something better. It's called Mini-Me. So I said, every process on an operating system should have a little OS process that shadows the other process. So for every Word application, there's a little mini Word application. And so every time something crashes in Windows or any other type of system, we always want to get a dump. We want to try and find out what happened at the time of the crash. But what if we had a little mini me that's running there too? And he's doing everything that Word's doing other than creating a document. He's just mimicking it. Oh, I see you're writing a document. I'm writing a document too. So that's why I said it. So, and then this little mini me process, when this crashes, mini me is still alive. He's still running there. And what's he doing? He's at the location he froze. So when you crashed and there was a disconnect, he's in the same position doing the same thing that you were doing when you failed. So we can now ask mini me, why are you standing like that? What's happening? So we have that state dump, but he's alive. He's still there. And he even might have a memory. He might be able to recall. He'll have an episodic memory, say, oh yeah, I remember doing that and that wasn't good. And next time the big guy comes on, the Word document comes up, or the word process, he goes, oh, I'm alive again. What happened? He goes to mini me. And he says, okay, what were you doing? I better not do that again. Or at least I have to try to use that as a reason to change or adapt my behavior. So we can actually have mini me computing everywhere. Every operating system should have little mini me shadow processes running. They're tiny, but they're just simulating all the others. And of course, you could have one big mini me that simulates many, but we could actually have a mini me computing environment. And then every time we want to see the production or look at systems, we just look at mini me's. We don't look at the real applications. Anytime computing, I can run my code or any type of code at offline, online, in a different space, in a different environment, different language, different runtime. If every machine has a binary protocol of this is what I do, here's my behavior, interpret it and simulate it in that machine, then that machine, whatever language is running in, can invoke that language. So now we have the ability to integrate offline or online, but external in a different space, but also offline at night. We can just play back systems and do it. So if you didn't do logging during the day, you could actually do your login at night. Let's say you didn't do your audit trail, you could run your simulation again. And you can actually, and every time you have a new capability, you can go back to past memories and say, I wonder if we actually had this new tool, but now applied it to past memories, and would that have seen stuff that we didn't see at the time? You come into production the first day, someone says, okay, you're going to relive production for the last 6 months in a few hours. You sit in a simulation that you run through the simulation machines. You watch your monitoring console, your standard one that you're always using, but all the machines are simulating all of the times that you failed, where production failed, not you failed. And then you could be asked is, keep watching it and see, can you learn something for it? Because of course, it's a bit like a movie where you watch a movie and you watch it again, and the next time you see another actor in the background, hey, I didn't see that actor the last time in the background. So you can actually watch it again and again, and it actually feels real. So you can still, your senses and your attention is still there. It doesn't feel like it's a chart and it's not moving. You feel like it's live, and you can start to train yourself, train your mind and your own predictive capabilities based on the same feedback if you were in fact there when you just became a new recruit. And it's a bit like Neo in the Matrix, where you download something and learn. You can get that this experience and the learning simply by looking at the simulation. We could all start to be. We could get everybody to work together, so we could actually get all these languages, and I only just put a few down there. We could actually beam them all into some system, whatever language it's in, and have them all working. See, that's the thing about microservices. Everybody wants to write a particular service, maybe in their preference language, like Ruby. I'm going to write this one in Ruby. I'm going to write this one in Java. I'm going to write this one in Scala. I'm going to write this one in Go. And then you say to yourself, how can I see them all together? But or how do I relate all of their behavior? Let's say one's calling the other over, HTTP or some other protocol. You want to be able to see their streaming, but see it in an environment where you're able to plug in. So you could actually have them all project over into a simulation that has the same, whatever language it is written in. My one is written in Java. And then you can have Java hooks that hook into JavaScript running, Ruby running, or any language. And I've already demonstrated Scala and Ruby and Java, and then Python is also, I have it with Jython, so we can stream it over in there. And you have code that gets fired based on that. So actually, it doesn't matter what language the execution is, as long as you can observe it. It's a bit like the observable universe. It becomes the polyglot or universe. No. So that was it. Okay, any questions?